Hello everyone, that's Angelo Corsaro from AgeLink, and today I will be talking to you about edge robotics with ROS2 and Zenoh. So let's start with some motivations. Why edge robotics, and what do we mean by edge robotics? What are those use cases that we are really trying to address? So some of the use cases that are emerging and really needs to be addressed are those in which you have potentially fleet of robots, imagine either in industrial, agricultural, or semi-automated or automated delivery, that you need to manage, monitor, and control from pretty much anywhere on the network. Because you could imagine that you might have some control center or cloud-based control center, or perhaps still going forward with the rise of edge computing, a little bit more decentralized or localized control center, monitoring center, and so on and so forth. So obviously that requires you to be able to reach all robots, get information out of them, potentially do some controlling, and so on and so forth. Another use case that we have investigated, and I guess we'll demonstrate pretty soon, is that of having vehicles that have a lower degree of autonomy. So they are not completely autonomous. They're relatively cheap, and perhaps in some emergencies, such as the COVID pandemic that we have experienced, under lockdown, what you would want to do is to use these vehicles to deliver food and medicinals. So in this case, potentially, you have already a constrained environment because there might not be many vehicles on the road. And you could leverage a high number of these semi-autonomous vehicles, potentially by controlling them through some form of edge infrastructure. And all of these applications starts to become more and more interesting also because of the combination of also 5G technologies coming like MEC and the semi-autonomous or level 2 or level 3 autonomous vehicles becoming more mainstream and more affordable. So all of this, obviously, if we talk about robots, it would be kind of silly not to mention ROS. Why? Well, because ROS is, as of today, potentially the most widely used open platform. In fact, it's an open source platform for robotics. ROS stands for the Robot Operating System, and it's not actually an operating system, but it's a set of software libraries and tools that were designed to really make it easy to build robotic application. One of the, let's say, biggest advantage of ROS is that comes equipped with lots of drivers for cameras, lidars, you name it, a state-of-the-art algorithm, and very powerful developer tools. So, in many cases, ROS is potentially the one-stop shop for your robotic application. Okay, and that's why it has seen a pretty massive adoption. Now we are member of we contribute to the ROS project as we contribute very massively to Eclipse IoT and Edge, we see its use growing and becoming quite ubiquitous. So what is the communication model at the foundation of ROS2? Because that was one of the major changes between ROS1 and ROS2. So ROS2, in order to avoid the centralized architecture imposed by the ROS1 communication stack, moved to DDS, the data distribution service. And so usually a robot application built in ROS is a collection of nodes, and these nodes communicate within a robot as well as across robots using DDS. DDS buys ROS with location transparency, and that's a very efficient mean of having robots communicating within a single, let's say, robot, which might be just a single computer or a few computers or boards connected by a fixed network, or across a wired network. So when we talk about DDS, as now we'll be talking about the challenges, it's important to make some statement. Well, I've been there, I've done that. Okay, I'm one of the guys that started the DDS standardization group. If you search myself in combination with DDS, you will see that I'm one of those who contributed lots of materials. I've co-authored almost all the standard. And already back in 2009, as the internet doesn't forget anything, this presentation shows that you can find on SlideShare, I was already raising concerns about the issues that we had for scaling DDS over a wider network. So what are the challenges that DDS poses us? Well, DDS, as I said before, it's very effective in supporting communication within a wired network, but the way in which its underlying protocol works makes it very hard. And we have developed products, we have worked on that for several years before saying, well, let's do something that works differently, because we need to support this kind of application in the most effective manner. So some of the challenges are really rooted in the very nature of the discovery protocol and the reliability protocol, okay? Essentially, in a nutshell, that doesn't allow for good scalability and doesn't support a symmetric system. Okay, just to give you a quick example, if you look at the DDS reliability protocol, every DDS writer runs a reliability protocol with every matching DDS reader, which means that potentially a small device being a DDS writer would have to run a reliability protocol and a reliability state for 1 million devices. So that doesn't really work. And that model is very hard to break, okay, without obviously coming up with something else that is not DDS. Last point, for how DDS works, it works best when you can leverage multicast, but multicast and Wi-Fi don't milk very well, or don't mix very well. As a consequence, there are some challenges there as well. So what did we do? So in the past few years, we've been working on a new technology that now is incubating in Eclipse called Zenoh. And as you can see from this diagram out of the Edge Native Working Group, Zenoh is, as of today, the protocol that was really designed and addressed and to address the requirements of edge computing, looking really at the continuum from the cloud down to the most constrained device that you could have on the edge. What is special about Zenoh? So we treasured really all our experience in DDS, and we treasured all the experience and the research that has happened in the past few years in the context of the next generation internet protocols on name data networking and content-centric networking. So what we tried to do in Zenoh was taking the best of both worlds and coming up with a unified set of abstraction that would allow us to deal with data at motion and data at rest, as well as distributed computation, and do that at internet scale, while being able to go from the cloud to the tiniest device that you can find, like a microcontroller. So as a result, we provide you with super efficient pub/sub, and I'll give you some number, distributed queries, and we have a wire efficiency that I think is the best on the market, because we have around 4 bytes overhead on the wire, besides what you're sending from an application level. If you compare that to any other protocol, you see that we are, in some cases, even 1 order of magnitude, or 20 or 30 times better than anything else. Okay. Last but not the least, we have really 2 layers within this stack. One that is really a networking layer, another one that provides an abstraction for geo-distributed storages that makes it very easy, once again, not only to diffuse data, but to do distributed query and fetch data in a completely location transparent manner. So what are some of the protocol highlights of Zenoh? In order to support asymmetric situation, in order to support the device that go under duty cycle and does sleep, in combination with providing push, publish, subscribe, as well as distributed query, it also allows you to have pool subscriber, and subscriber that in general can negotiate a time schedule with infrastructure. We use resources like in NDN, they look like URI, but obviously if you want to be wire efficient, you do not want to send this string over the network. At the same time, like other protocols do, what you do not want to do is to map this string explicitly to integers, because all of a sudden, if you have to map this string globally to integers, that becomes a configuration nightmare. So we do automatic mapping of strings to integer, that completely transparent, it's done end-to-end, and it's always a local decision. So we have very good wire efficiency and usability and ease of configuration. In terms of communication topology, we support peer-to-peer, routed communication, and then we can have pure client that use either a peer to route data or connect to a routing infrastructure. We support order data delivery and fragmentation. Okay, so that's very important. And the minimal wire overhead is 4 bytes, as I mentioned before. So how does it look in terms of performance? Because this is a protocol that, as I said, is able to go from very small device, but yet also function as a backbone protocol, because we really want to give a solution that can work end to end, and that was one of the intent of our design. So you can try performance yourself. This is the recipe on how to try the performance. Just check out our Eclipse Zenoh repository, build it, and then we have distribution in the distribution test to measure performance. What you see here is performance within a host and then across a network with a 10 gigabit network. The host were equipped running Linux and running over some AMD Ryzen 8 board. What you can see is that from this graph is that essentially we saturate a 10 gigabit network at 1024. Well, you will discover that. But let's say for small data, we can easily push around 1.3 million messages per second. And by the way, I recommend you take a look at the example code for our throughput, because it is exactly how you would write it after having read the hello world or the getting started. There are no tricks in the code. It's run right at the time in a tight loop. That's all it is, okay? And I think it's very important because we want to measure performance that you can easily achieve in your application. So once again, for small data, you see that we are very effective in our protocol implementation to ship that across. And if we look at the brokered or the routed situation, so when communicating not peer-to-peer, so in this case, we have an extra hop and we have a router running once again on a machine with two 10G network interfaces. So it's really, there is an inbound and outbound interface. Here you see that the throughput goes a little bit below. We are around 900,000 messages per second for small data, and that eventually goes down inevitably because the bandwidth is limited. If we look at throughput, okay, of the three different cases, I think there are two things that are important. First of all, we saturate already a gigabit network at 128 bytes payload, and we saturate a 10G network or a 10G Ethernet at 1024 bytes for the peer-to-peer and 2000 bytes for the routed. So I think those are pretty impressive performance. You feel free to compare us against any other mainstream technology. Our measurements show that most of the time, if not all the time, we are on top. So in terms of architecture, Zenoh is structured into two layers. As I was mentioned before, there is something we call ZenoNet, that is just a networking protocol that, by the way, can sit on top of a data link. So we don't need IP. We can run easily over IP. In some instances, we cannot afford to run over IP because it takes too much overhead. Or in some other instances, there is no IP network, and we are used as the bootstrap communication mechanism to then provision the IP network. In any case, either for one or the other reason, the good point to know is that as we have our own routing, we can just sit on top of a data link, okay? Our ZenoNet provides us essentially with the key abstraction on top of which we build higher level abstraction that are included as part of Zenoh. And those include essentially primitives for PubSub, primitive for distributing and consolidating queries, and support for fragmentation and order delivery. Let me actually go a little bit. Yeah, I think actually, let me go back one moment. So in terms of the protocol structure, the networking protocol is really made by three subprotocols. There is a scouting, a session, and then the higher level ZenoNet protocol, where the session is really what allows us to do all network scheduling, because we do quite some advanced network scheduling, and easily port Zenoh, as well as shield the ZenoNet higher level protocol from the specific of the network on which we are sitting. The scouting protocol is also pluggable, and obviously we would have different scouting protocol depending on the network, because as you can imagine, the way in which we might do scouting over an IP network or over Bluetooth is not at all the same. Okay, so if we focus for a moment on the publish subscribe primitives that we provide push as well as pull subscriber. So pull subscriber, essentially, they are regular subscriber that just tell to the infrastructure, look, although I would like data to be delivered as close as possible to me, don't push it to me because I'll tell you when I'm ready, or I'll agree with you a time schedule, and you are allowed to push me that time schedule within to push me data within that time schedule, or I'm telling you that I will be asking you data within that time schedule. And that obviously allows us to do optimization on how and when we bring data so that it's typically just one hop away. So if we were to visualize all of these, at the lower bottom left, you see a device that is sleeping. So that's a pool subscriber. So in this case, whenever there is a publication, data is distributed by Zenoh to all subscribers, and storages for us are a subscriber, and as we will see, a queryable entity. And you see that Zenoh try to get data as close as possible to pool subscriber. When then a pool subscriber wakes up, he pulls the data that typically is just one hop away, and then goes back to sleep. When issuing a query, this query is distributed to the set of queryable, because that's one of the concept we have in Zenoh, that is optimal with respect to the distance and optimal with respect to the coverage of the query. And for that, we have essentially a constrained set coverage algorithm that we run to identify which are the ideal storage where we should go and fetch the data in such a way that, that we can have a complete set to answer our query, if such a set exists. There are some options that allow also potentially to do quorums, but I don't have the time to go in details. For what concerns routing, we have adaptive, fault-tolerant, and multi-domain routing. Multi-domain routing is essential if you want to scale. And more importantly, the routing approach and the topology that makes sense in different domains when you are really running over a large scale is very different, right? I mean, if you think really about an end-to-end application from the data center down to the cloud, you might think that in some area you want to have click, in some other area you have arbitrary mesh, or hub and spoke, and so on and so forth. So we support multi-domain and generalized routing. So transparently, based on the topology that you make possible for your system, we'll use it at best. Okay, so how does a Zenoh application looks like? So here you have a publisher in which you see that you open a session, you declare a resource, you declare a publisher. By the way, resource declaration, publisher declaration are optional. And we use resource declaration just as an optimization step to force, in a way, or give you a chance to force a mapping, an implicit mapping potentially to an integer. Otherwise, we do lazy mapping internally, okay, if you don't register explicitly. And then you see that there is a write, and you close the session, done. How about the subscriber? So again, that's some code in Rust. You see that you open your session, you define the kind of your subscriber. So in this case, a reliable subscriber, which is asking to be pushed data all the time. So it doesn't specify a schedule. You declare your subscriber, and then look at this. Essentially, you can stream data through your subscriber. So we support two ways of getting data. You can use streams, or you can use, old-fashioned callback, which introduce obviously inversion of control. But this is far. I think it's it's usually nicer to be able to avoid inversion of control and using this kind of API. Obviously, we do not support only Rust. We have just released the rewrite of Zenoh that is entirely written in Rust, but we have obviously API for Python, C, C++, and so on and so forth. So what is the status of Eclipse Zenoh? So we have just released, in fact, I think it was 2 weeks ago, Zenoh I2. Okay, that's a full rewrite of our Zenoh infrastructure that now introduces generalized peer-to-peer, client-to-router, or peer communication. We have improved our linked and routing algorithm, so that has improved our throughput, and by the way, has also improved our path selection. We have released a DDS to ROS2 plugin, and which is what I will demonstrate also as part of this presentation. And we have API in Rust, obviously C++, Python, and REST, and amazing performance. What's coming up? We're about to release Zenoh Pico, which is a C-based stack of Zenoh for Pico devices, so super small devices. We wanted to get them through Rust, but Rust embedded, it's very cool, but not yet exactly where we would like it to be, especially on OS like FreeRTOS. And I think we also, from the Eclipse developer survey, how FreeRTOS is an important OS for our domain. We are going to add Golang and Java, TLS. We have already, but it's not yet released, but you can play around with it, both an RMW for ROS2 and micro ROS, but we'll be releasing the one for micro ROS. We'll be adding more storage backend for InfluxDB and file system, and looking forward to integration with Eclipse Isorix and in general zero copy. Okay. So if we put all of this together, essentially, you see that now, thanks to the nature of Zenoh, right, you can use Zenoh in combination with ROS to avoid all the challenges on Wi-Fi. You can use the Zenoh plugin for DDS, as DDS is the default transport for ROS, to bridge your robots or your ROS, based autonomous vehicle, whatever it is, essentially very efficiently through the internet. Additionally, and I've had not much time to explain all the distributed storage functionality supported by ROS, but additionally, if you think about it for a moment, once you have ROS data in Zenoh, you can decide where the data should be stored, could be stored potentially on the edge, very close to your fleet, and then you can use Zenoh distributed queries potentially to query that data as opposed to just have it push it to you. Okay, so what I want to do now essentially is to demonstrate all of this, because it's good to show slides, but it's better to show working code, and I think that's our motto, I think, at Eclipse Foundation, which is code is what matters. So what I'm going to show now, I will have essentially 3 machines. One is a machine that is sitting here with me, a Linux box called Snoopy, in which we will have running a ROS application and a Zenoh router with a ROS2 plugin, so it's a DDS plugin. Then I will have we will establish a connection between our Zenoh router here and a Zenoh infrastructure running on the internet. Okay. And on another machine that is running, again, in that case, I'm in Paris. This machine, I believe, is in Hamburg or somewhere in Germany. We will start also another ROS application and our Zenoh bridge. And you will see how a ROS application will be able to flow across the internet. Okay, so let's do that. So let me change desktop. So you can see this is the IP address of Rio, which is a machine, again, it's a Linode. This one should be somewhere in UK. Then Gohan is in Germany, I believe in Hamburg. And Snoopy, you can see it's actually not a public address. That's Linux box that is just sitting by my Mac. Okay, so just to make things simple, we have a full infrastructure running, but I think it's simpler to show you what happens in this case. So we start a Zenoh router on this machine. What we do here, we start a Zenoh router, and I'm asking to print the log because I will show you something interesting, in which I provide the locator of our, so the entry point for this infrastructure, right? And in this case, I'm saying that I want to scope any ROS traffic with this prefix, because imagine that I have different subsystem, and as you will see, most of the time ROS uses similar name. So if I want to distinguish those, I can add artificially a prefix when mapping ROS DDS topics to Zenoh resources. So let's start this one. Here you will see a few logs. You see that it discovers actually its own DDS participants. Okay, and if I start here a ROS listener, okay, with this ROS command here, now what you will see is that this DDS plugin for Zenoh has discovered the listener, has discovered a series of DDS topics and has mapped those into Zenoh resources. Okay, so these are the Zenoh resources in which they were mapped. And you see that our prefix is being used to ensure that potentially we don't have conflict if we have multiple subsystems exposing the same data that we want to isolate. Again, that's an option. You are not forced to pass necessarily a prefix. So the listener is listening, but nobody is talking. So what we are going to do is that on Gohan, which again, as I said, it's running in, I think this one is in Germany. Let's start a talker, okay? So if I start a talker, Now you see that Snoopy is getting this. So let's start now a listener here. Now you see that the local listener obviously is also getting the local information. And if I start a talker on Snoopy, now you see that both listeners are getting both information. You should see that from the sequence number here, okay, on the ROS application. So what is interesting here? Well, obviously, you notice that the loops are being avoided, right? That's already important because when you have pub sub, already in this situation, there are a few loops that have been created. And you notice that this is completely transparent for the application. Nothing was changed to the ROS application. If this were, we can do this with physical robots, we can distribute video, you can do anything. And it's completely transparent. You can decide what to expose, what not to expose, and so on and so forth. Okay, so successful demo. At this point, let's go back to the slide. And that was it for my presentation. I think we are good with time, and I believe we should have a few minutes for some questions. Okay, so I understand minimal overhead. What is the typical overhead? Okay, so essentially, the typical overhead depends on the Zenoh configuration. Why? One of the lengthy discussion we had was, what is the right sequence number, right? Because if you're running on a constrained network like BLE or ZigBee, you want to have a small sequence number. If you're running over a satellite link, the same sequence number that would make sense on the network doesn't make sense on a satellite, because you want to have lots of packets in flight. So in that respect, we negotiate sequence numbers when establishing a session, and that is what controls, between other things, the wire overhead. So when using the 1 byte sequence number, in that case, our wire overhead, it's 4 bytes, right? If you use 2 bytes because you need 2 bytes, then it becomes 5, and so on and so forth, okay? So there are some configurable parameters that impose, let's say, the minimum sequence number. For what concerns resource ID, let's say that as far as on a single application, you are not using more than 128 resources, then you have only 1 byte to represent the resource ID, which is completely locally unique. As soon as you use more, then you have 2 bytes, and so on and so forth, okay? But you see, typically an application, it's rare that a constrained application will operate over 128 resources. And again, the binding between the string and the integer is completely local. So I hope that gives you some idea. Other question, is Zenoh data agnostic? So ZenoNet is absolutely data agnostic. On the higher level, so the Zenoh layer, we support multiple encodings. The number of encodings supported is open-ended, and we have transcoding between those encodings. We do not support IDL as of today, okay, but we support JSON properties and relational representation. Okay, so typical query supported by Zenoh, think of it, okay, I have still 1 minute, so maybe I can quickly show it. Well, let me do like this. A typical query has 3 elements. One element is the key selector. That's an expression that selects the set of keys that you want to query. Then there is a predicate. A predicate speculates on the content of the data. And then we have a projection. Okay, so you select the set of keys. Out of the set of keys, you select the data that validates the predicate. And out of that data, then you project the attribute that are in the projection. So that's, in our experience, quite powerful, because sometimes you don't want to recover all the data, but for some data set that satisfies some predicate, you just want to project a few attributes. And that's something you can do with Zenoh. I guess we are done with time. Not sure if there are any other questions. Otherwise, thank you very much for your attention. And well, give it a try and let us know. Thank you, everyone. Bye-bye.